by Babis Anastasiou, who is visiting from ETH. Later Simon will talk, but Babis will tell us about two-loop amplitudes. I think he's been soft on us. No, Babis can do like 10 loops, but, but we're normal human here. So.
Okay, so thank you very much for having me here. It's actually very nice to also to see you again, Sergey, after some time. So today I would like to talk about a little bit of a change of direction or change of hearts that I had with myself in QCD, and change of approach. So if you remember, I could do many loops. Now I have to go back to 2 loops because I think it's about time to think differently about this whole problem of computing QCD amplitudes, if we want to meet the challenges of the future. So I will talk about work which I have initiated after a very nice visit of George Sterman in Zurich, where I asked him one thing and he answered to me something better. And then we started working in this direction. And in the meantime, we also had the luck to have great people, younger people, to join us in this exploration. So by now the program is underway, and I would be very pleased to tell you what this is about. But let me start a little bit about the traditional approach of how we do calculations of QFT amplitudes. And it can be electroweak, it can be QCD, it can be mixed, whatever type you want. And at higher loops, because of the fact that these QCD amplitudes or massless gauge theory amplitudes contained in them, they have divergences, both infrared and ultraviolet. We have learned to do calculations using the measure regularization or some type of regularization. And because of that, because you have an analytic parameter sitting in your expression for your amplitudes, you are biased towards analytical calculations. Okay? The program of computing analytic amplitudes is very successful. We have arrived to huge successes in this way as a community. But I would like to tell you a few things that one can observe by going in this analytical path. At one loop, the analytical structure is beautiful, simple, and completely constrained, no matter how many legs, how many external particles you scatter at one loop. So if you take any QFT amplitude in 4 dimensions, and you write its analytical expression, you will find constants, you will find logarithm, you will find logarithm square, and you will find only one kind of funny function, which is called the di-logarithm, and nothing more. Of course, the arguments of these logarithms can vary depending on the kinematics and reflecting the cut structure and discontinuity structure of the scattering. What is more, the coefficients of this amplitude, of these functions, they are beautifully expressed with progress in the last 2 decades as sums of products of 3-level amplitudes. So give to somebody any scattering problem at one loop, they will be able to even guess the answer about what the amplitude is. Okay, so this is a very huge success of the analytical path. Now, let's go at 2 loops, and the story changes. Okay, so the first time that we looked at scattering at 2 loops back in 2000, we discovered that we didn't have only the di-logarithm, we had the tri-logarithm, the quadrilogarithm, and one more special function to describe all 2-to-2 massless QCD scattering. Then people wanted to put some offset external leg, like doing a Higgs or a Z in the final state, and this basis of functions extended a bit more. But still it was very systematic and nice. And then came more complicated kinematics, where you have 2 offshell particles in the final state, 2 W's or 2 Z's, and again, people discovered that they could generalize the structure of polylogarithms to a bigger class with a lot of algebra properties in there, which were very constraining and nice. So because of this, now we have, now means something like 8-10 years ago, we have the boson cross sections computed at next to next leading order.
So this is already at finite mass. You're not talking about, because you started with massless theories. So.
Massless theories, but the W's and the Z's, of course, are physical W's and Z's. Okay. When we did the Higgs cross sections and the NNLO, we actually did not do it faithfully. We did some expansions, but the underlying integrals were a generalization of polylogarithms, of what is called elliptic polylogarithms. And this is a new species of analytical functions, which are, of course, very well studied, not very well, very intensively studied by both mathematicians and physicists, but the full structure is not really understood. These functions also appear when one looks at string theory amplitudes.
I make a very naive question. So is it related to the fact that these logarithms and all these things, they admit some integral representation that are similar to the one you do when you do loop diagrams, or maybe some different?
If they admit an integral representation which is similar to the Feynman parameterization, you mean?
Yeah. To the basically the integrals you do when you solve the two loop basically, what's the reason why they come this dig out to those?
Why do they appear?
Yeah.
Well, if you start from, they appear in many different ways. You can build you can build a higher complexity integral from a lower complexity integral. For example, you can add an external leg by, for example, integrating over the lower external integral, integrating over a kernel which involves the simpler integral. And if the simplest integrals are polylogarithms, simple polylogarithms, then you have this kernel that you integrate upon, and then it gives you the next rank polylogarithm. So this is one way to see it. I'm sure that people see it in many different ways. If you start with Feynman parameterizations, there are papers that they tell you that these Feynman parameter integrals belong to some mathematical class which is called periods, and some of the results that you expect from these periods are polylogarithms. Okay, but what I want to say is that this structure that comes out of Feynman integrals in amplitudes is much more general than what we have explored mathematically. So what is happening here is that it's not clear, if we take any arbitrary two-loop amplitude, that we can map them to some finite set of functions, that they also obey nice properties that they allow us to evaluate them. So the analytical approach seems to be very rich, a little bit too rich from what we can have, or at least what I can. And now the question is analytical approach going to get us to the next level of amplitudes that we need for physics, for phenomenology? So I want to show you a few results where this analytical approach seems to be struggling very much, and it seems intractable, is when we go to 2 to 3 processes at the LHC, like, for example, the process for producing a top pair together a Higgs boson. This has been measured at the LHC already, and right now the uncertainties are big, but eventually we will reach at the high luminosity phase a 5% precision in determining the top anti-top Higgs coupling directly from this process. And in order to match that, we would like to have this process where we produce 3 heavy objects in the final state at 2 loops. So analytically, nobody hopes that we can actually do it. Another example that I will mention it simply because this is what we started investigating first as a test case, is triple gauge boson production. This is a very rare process, but already it is measured at the LHC. But it's again intractable analytically. It offers actually very beautiful information because, you know, you can test a quartic gauge, electroweak gauge coupling in this process directly, while in other ways it's not easy. So there are motivations to stop with this analytical method approach and try other things if this doesn't work. I also want to advertise a little bit, since you are, you know, world experts in cosmology as well, to advertise that when we learn things in QCD, they don't just stay in QCD. You can have applications also to cosmologies. I'm sure you have heard talks about gravitational waves and how the amplitudes program has helped to calculate waveforms for gravitational waves. Another recent application that I have started with a new collaborator at ETH, Leonardo Senatore, and bright students of his, is to try to map integrals of the effective field theory of the large-scale structure to QFT integrals. We managed to do that analytically at one loop. We actually can calculate any correlation function at one loop in this CFT in a closed form. But if we want to go to two loops, which we are doing right now, we are encountering integrals like this with many masses inside. And since we have many scales, the analytical approach does not work all the way through. So at some point, for some integrals, which we call master integrals, we will have to evaluate things numerically. So even in cosmology, the analytical approach cannot go all the way to the end. So I would like to see if we can do things numerically, but it's not as easy as that, because as we discussed at the beginning, there are singularities. These singularities are completely entangled, and the major difficulty that we have is that to remove these singularities in a systematic way. So I would like to describe how this could go along. I should not declare any victory. We don't have any serious physics application yet, but I hope that we have set the foundations, and I hope that very soon we will be able to produce cross-sections and amplitudes on the computer. So today I will focus on the theoretical background. To be able to do things numerically, we have to remove the singularities from the amplitudes. And there are three types of amplitude of singularities. One of them is ultraviolet singularities that one can remove with the DPHZ approach, even locally, nicely. Another type of singularities are infrared singularities. In physical cross-sections, they either cancel or they help to redefine photon densities or fragmentation functions for finite cross-sections. And finally, there are some other integrable singularities, which we call cut singularities or threshold singularities. For example, if you compute an amplitude, for example, like blue blue to Higgs, you will see that for some masses, like if you take the offsetness of the Higgs boson to be twice the mass of the top, you see some extra growths and so on. So these are reflected in the analytical structure of the amplitude, and they originate from integrable singularities, but integrable which are not, but they have discontinuities. So these are the three types of singularities that we have. Let's see at the level of the integrand how these singularities emerge, and I will focus mostly on the threshold singularities and on the infrared singularities. So amplitudes contain propagators. Propagators have denominators which are of this form, and they produce poles. So if you have one propagator, you will create a pair of poles because of this propagator. Now, in general, these poles do not destroy the convergence of the integral. So these poles can often be avoided by a contour deformation. So if this is a situation, these poles let your integral live in 4 dimensions. And if you figure out the contour deformation, you can integrate numerically over the contour. But in massless gauge theories, we can have situations where particles become soft, and then the poles align one on top of the other and pinch the contour of integration. So then you are not permitted to deform the contour up or down, and this singularity is a true potential singularity for your integral. If you have collinear particles, this is another situation. One massless particle splitting into 2 massless particles, then one pole from one propagator aligns on top of another pole from another propagator, and then again you have what we call a pinching of the contour, and then you are not allowed to deform away. So whenever you have pinch singularities, these are the infrared, true infrared singularities, you cannot deform away of them with a contour deformation. So what do you do then? Well, first of all, there may be something else that saves you. It may be that the degree of divergence of these singularities is not high, so these things may still be integrable. So you have to figure out a way to quantify whether such a singularity produces indeed a divergence. The way to do it is to identify in your integration domain, represented by this cube, where the singularity surface lays on, and then to parameterize locally on the integration variables as variables that they are parallel to the surface and vertical to the surface, and then to rescale the vertical coordinates by a parameter and study the behavior as this parameter goes to 0. Then this tells you how strongly this singularity develops as a part of delta, and in exactly the same way as you would do for ultraviolet renormalization, you can have a degree of divergence and see whether such a singularity is there or not. Now, we know, let me summarize. We know where the poles of the integrand are. We know when these poles can give pinchings, and this is corresponding to soft or collinear particles. And we know to calculate whether this will indeed spoil or not spoil the convergence of the integrand. Okay? So if we have a convergence situation, a divergence situation, and if we only have one of such singularities, the situation is quite simple. What you can do is you start with your integrand, then you remove from it an approximation. T means an approximation of the integrand on the singular surface. And this approximation can be simple, and I will talk a bit about it later. Then this difference can be computed in exactly 4 dimensions. Now the rest, you have to put it back. And I will tell you that it is simpler, because it corresponds to a singular approximation, to a singularity. Some physics comes into it, and the rest becomes simple. So simple things, we will do them analytically. Complicated things, we will form these subtractions and we will do them numerically. So this is the idea. Now, what I described here is a situation that you only have one singular surface. But in loop integrals, the singularities are entangled. You have many of them. So what do you do then? And luckily, there is the traditional work of Sperman, Collins, and Soppers, and others later on, that they have discovered, no matter how complicated the overlapping, the entanglement of the singularities is, they discovered a criterion how to subtract all the way to the end so that there is a finite remainder of any loop integral. So the idea is this. Suppose you have your integration domain. Suppose you have many singularities. I represent only two, one with red and one with blue. Now, you can think of this singularity, which is localized to a point, as a soft singularity. If a particle becomes soft, its momentum is 0. This corresponds to one point in phase space. Okay? And this can be something like a collinear singularity. And at an endpoint of a collinear singularity, a collinear particle can also become a soft particle. So they overlap. Okay? So the criterion is the following. You start with your integrand, and you subtract an approximation of the singularity which occupies the smallest volume within your integration domain. So in this case means the soft. Then after you subtract that, on the already soft subtracted integrand, you make a further approximation and you subtract the next one. And you continue like this, subtracting first the smallest volumes and you continue to the highest volumes. So if you classify the singularities about how extended they are in the integration domain, successively, starting from the smallest, going to the biggest, you can subtract all of them. And all of this can be systematized in a kind of a Forest formula similar to what one sees for ultraviolet organisms. But let me give you a picture when you apply this procedure in every integral in an arbitrary QCD alpha. Then, this picture is an all orders picture, at all orders interpretation. Then you can prove the following. Not easily, these people have really done marvelous works to prove it at all orders perturbation. Then you can prove that your amplitude for a scattering can be decomposed into factors. Factors that they depend on the external legs and they contain the singularities. Collinear singularities are contained in factors that they correspond to each external leg, and we call them jets. And soft singularities, they correspond to the soft function. It connects in color all of these regions, all of these external legs. So this can be thought as a matrix in color space, and it knows about pairs or triplets of particles and so on, but it is a factor. So let me show something more concrete beyond the picture. At all orders perturbation theory, an amplitude should be in color space a product of the following: a hard function which knows about the process and describes the short time interactions, and infrared functions, the soft and jets, which describe soft exchanges and collinear exchanges. Okay? So this is what we can prove exactly at all orders in perturbation theory. It's not an approximation, this is an exact one.
Yeah. So you kind of explain it at the level of dealing with integrals, but is it kind of what, like soft collinear effective series? Is that what it also does? Like
soft collinear effective theory has exactly this picture, absolutely correct. They arrive to it differently than the factorization of Steinman and so on. What I would like to do is to go again through these proofs of factorization via QCD factorization or soft conveyor effective theory and make it in a different way, so that this will give me so that I can have locality on top of the proofs. In other words, the hard for soft conveyor effective theory is a Wilson coefficient, and the interactions of jets and soft particles is the fields of your effective theory. So this Wilson coefficient can be computed by a matching, by integrating out degrees of freedom. Okay? But when you do that, this is not a local object. And what I want to make sure is that this is a local object that I can directly compute. I will say a few more words about it. But you are absolutely right. The same picture comes out from soft conveyor effective theory. Okay.
But I'm just trying to understand what you're doing. Is it just in different language exactly the same thing, or you really?
Give me one page, and I will probably try to understand.
I'm just basically following up. I mean, soft conveyor effective theory, at least the presentations I've seen of it, it's not presented as like a local field theory in the usual.
Exactly, it's
right.
not local.
I mean, it's all in like Fourier space or whatever. So you're presenting a version of this story which makes locality sort of manifest.
Locality in momentum space.
Locality in
So
momentum space.
sorry, yeah, I won't. But in one page we can come back to these two questions, and I hope it will be a little bit easy. Okay. So okay, how can I imagine using this picture? So as we said, what we care about in physical cross-sections is the hard scattering matrix elements, one of the factors. All the jet functions and the soft functions, they find their way into cancellations or absorbing into parton densities or fragmentation functions. So what we would like to do is to take the amplitude, multiply it with the inverse factors, and remove our singularities. Okay? So this is the big idea. And now come a little bit in a language of integrals and defining exactly what Simon was asking about my space. So what I want to do is this theorem works in momentum space. Okay. So practically, if I have an amplitude, then I have to integrate over all virtual momenta of an integrand. And what I want to say is that this amplitude is the same, but separated into two pieces. One piece which has the soft and collinear singularities, and one piece that does not have it. But now you can view all of these factors here, which are one the inverse of the other. You can view them as local functions in momentum space, K. So, and what you want them to do is to cancel the singularities of the amplitude. If this is done in such a way so that point by point in the integration domain, the singularity of A, the integrand of the amplitude, is matched by the singularities here, then this object can be numerically integrated in the equals form. Okay? I will show you exactly where the problem is, and you cannot do it with soft conveyor effective theory because it does a few things that they are not useful. So
like trivial UV singularities. Yeah.
Also, I should treat the UV singularity. So in all of these, I should make subtractions for local subtractions for UV. I will talk a little bit at the end. It's a simpler situation. There is a small complication, but I don't need to care very much about if I solve the infrared, then the UV will be cruising. Okay. Now, what I want to say is that all of these factors they are series in our perturbative coupling. So if you take this integrand and you expand it out in alpha strong, then this will give you order by order in perturbation theory some amplitude minus factors that you subtract, and they make the amplitude finite. So at leading order, the hard function is the 3-level amplitude. At next to leading order, the hard function is the 1-loop amplitude minus some jet functions hitting on the 3 amplitude, or soft functions hitting on the 3 amplitude, and so on and so forth. So this, you see it up in the factorized form at all orders of perturbation theory, but when you truncate, you have to expand in alpha strong, and it takes the form of subtractions. So, okay. What is really the problem? Why can we not just take the old theorems, including soft collinear effective field theory, and do it? The problem is what I call non-localities. Okay? It is true that all the singularities that you have in the amplitude are contained in the jet functions. But you don't want them to be at different points in your integration domain. So if this multiplication with inverse jet and soft functions gives you something finite, but the singularity of the soft is not aligned with the singularity of the amplitude in momentum space, then the Monte Carlo will never do that. Numerically, you cannot integrate that. So you have a plus infinity in one point, a minus infinity in another point. This is not how you should do it. So you have to bring all the singularities to be aligned one on top of the other. Okay? And this is where locality, or at least what I call locality, is important. Point by point at the integrand, we have to make sure that this works. Okay, so what I want to say is that this is definitely not a trivial thing, and I will explain why. But I wanted to report that we had a first success. And the success is that if we look at quark, anti-quark annihilation to any electroweak state, so you can put 1,000,000 W bosons or Z bosons in the final state, then we can make all of these amplitudes to be locally finite and integrable in 4 dimensions by subtracting at the same time all soft, collinear, and ultraviolet singularities. And these cancellations should take place point by point in the integration domain. So these are how these amplitudes look like. You can see gluon exchanges. But before I tell you how this works at 2 loops, which is the new result, I think I should explain how this works in a simpler setup, which is the 1 loop, and then I can tell you what is the difficulty beyond 1. Okay, so let's see this. So from now on, I will talk about electroweak production. If you look at the production of one photon, one virtual photon, via quark anti-quark, and you look at the soft limit, then we all know that what comes out is an iconal factor times the 3-level amplitude. And this is the factorization, which is also anticipated by the factorization theorem. What does it mean? That if you complicate the final state and you put 2 W's and a Z boson, and you look at gain at the same soft limit, you will find the same form factor, you'll find the same iconal factor, times now a different 3 amplitude, which corresponds to the new process. So factorization of soft singularities, it's actually almost immediate. You don't need to do much to solve. Now let's go and look at 1-loop collinear singularities. Okay? So let's abstract it a bit. Imagine that you have an external particle, it splits into two collinear particles, and these are the rest of this blob represents the rest of the amplitude. So this can be many Feynman diagrams, but all of them, they will have these lines in common. Now, let's put in the Feynman rules for this expression. The dots represent the blob. There is a fermion propagator. Oh, sorry, this would have been P plus K, but it doesn't matter. Here there's a minus sign. But so this is the fermion propagator. And there is also a gluon propagator, which is here. And there is this vertex, which is the gamma mu, and there is a spinor, which is there. Now let me take this in the collinear limit, where the momentum k is parallel to the external momentum p. Then both these guys, they become proportional to the argument of the spinor. So what you can do now is you can anti-commute, and then the whole thing simplifies. What you get is k mu, which is x times p mu, times the factor. Now, how can we interpret this k mu? This k mu, we can interpret it as a gluon entering an amplitude made of the subgraphs with a polarization which is longitudinal. So, okay, what does it mean that in the collinear limit we have a longitudinal polarization? It means that word identities and gauge theory can come into play and help us see that some cancellation take place. So suppose you have, we all know this three-level word identity. If you have a quark and quark vertex and you contract it with some longitudinal polarized gluon, which I will indicate with an arrow, then this vertex becomes a difference of two propagators. Okay? And the same thing happens if you go to the triple gluon vertex of QCD. You have a few more terms, which we call ghost terms, but the spirit is exactly the same. So the word identity at the tree level is as simple as that. Vertices become differences of propagators. When you take a collinear gluon and you consider all Feynman diagrams that this collinear singularity can occur, so let's take the example of WW production. Then you will have the collinear gluon, longitudinal polarized, attached here and here. Then you can apply the fact that vertices become differences of propagators, and then you get many terms, and then you see cancellations. This term originates from this Feynman diagram, these two terms originate from this Feynman diagram, but here you have a cancellation. And what you are left over is a correction to an external length. So when you have collinear gluons, they correspond to longitudinal polarizations, and at the end of the day, what they do is they give you a factorized contribution, which is a correction to the external length. And this is what the factorization theorem actually tells us. It tells us that we can take the Feynman diagrams, all of them, and we can look at the singularities, and we will find a correction to external lengths, which is a collinear singularity, and an iconal factor correction, which is the soft singularity. Now, all of this happened locally. So if I take this expression with the limits that I just computed before, then I will see that point by point in K space, the singularities of this expression match the singularities of my Feynman diagram. So I can subtract the two and get something finite. Okay? So this is what happens at one loop. Now we can even be a bit more clever than that. And I hope I can be on time with this. We don't actually need to subtract all these factors enumerating what is soft or collinear singularity. We can just use the fact that these factors are universal for all processes. Okay? So suppose I have an amplitude, one loop amplitude, which has many gauge bosons in the final state, and I will find that the singularities are what I just told you from the factorization. But now let me take the 2 to 1 amplitude, where I have some funny vertex here, some composite operator vertex. This is only 2 Feynman diagrams up to 1 loop order, and this one will have exactly the same singular structure. So now if I subtract the two, and I tune this effective vertex to be the 3-level amplitude of that, then I will arrive to something IR finite. So this is the logic that since we have factorization, we have universality, and we can use the simplest process in the class to cancel all the singularities of all more complicated processes. Now, 2 to 1 processes, form factors, we know them up to 3 loops pretty well, and even 4 loops nowadays in some parts. So we can, if we can generalize this project beyond 1 loop, then we can subtract all the singularities locally and arrive to finite integrals. So this is the 1 loop story. I don't know how complicated or simple it was, but if there are questions on that, please.
So just we go. How is it possible to prove that at any loop you would have this structure? The main idea.
How it is. So the main idea is actually starting with all Feynman diagrams and looking. First of all, you need to know how many of your singularities you have, what types of singularities. And this is enumerable with this analysis at the beginning of where the poles are and what is the degree of divergence. So this is one thing. So you know all types of singularities that they may ever appear at any order in the theory. And this has already been proved in the 70s and 80s. Once you have done that, then you need what I described a nested subtraction where you start with the smallest volume singularity and you go to the highest volume, and you make sure that when you do it in this order, nothing is left over, which is singular, and therefore you have something finite. And then, once you have all of these singular factors, identified for every integral, then you have to combine them together. Okay? So, in other words, for every Feynman diagram of any order in perturbation theory, I can identify locally, in fact, what are the singularities and can remove them. They don't give you these factors. In order now to see that they give you these factors, you need to use word identities. You need to use cancellations from one diagram to the other of the collinear singularities. And the proof that is used is that the sum, practically, they map all the collinear singularities to the terms that the word identity wants to put together to cancel. And what is left over after these cancellations is only corrections to externalities. In other words, power counting, removing the singularities sequentially in an iterated way, and gauge theory word identities to show you that essentially longitudinal degrees of freedom are expelled. So this is the bottom line. Something a gauge boson, which is a massless gauge boson, which is longitudinal, if it forms an amplitude, if it's an external electron amplitude, should give you 0. And in what I have here, you don't get a full amplitude that gives you 0. It just there is something left over which gives you the factorized term. I don't know if this makes sense. But gauge theory, gauge invariance is the main tool for organizing into factors. Okay, so now let me talk a little bit about locality. Okay, what I did before is to draw down the Feynman diagrams, and I just looked at their soft singularities and collinear singularities, and I saw that they map exactly to this picture. And I also told you that point by point, these factors match the singularities. Okay? Could I make it in a way so that this doesn't come out as a result? Can I destroy it? And the answer is yes. I could destroy the cancellations that I have in the word identity if a collinear gluon in one Feynman diagram has one loop momentum, and in another Feynman diagram it is shifted or reversed or is labeled differently. Okay? So if I take you the original, here every gluon has momentum k. But if I now take one of the Feynman diagrams and say, oh, you know, I live inside an integral, so let me shift myself by something, then these beautiful cancellations from one diagram to the other, they are going to be spoiled. So that's why it's important to have locality. And in fact, what this calls for is conventions for how to write the integrand of amplitudes so that factorization emerges. So then at one loop, we have to be silly not to achieve it. We have to really do something unnatural to spoil locality. It came out immediately out. But at two loops, we have to be actually a little bit more thoughtful in order to make it come out. And I can tell you with words what are the problems that we have. So at two loops, first of all, we will have to think hard how to give loop momenta labels, how to assign momentum flows into the diagrams. The other thing that we will find out is that if you look at the word identity at one loop, so if you have a collinear gluon, if you have a longitudinal photon attached to every position in an amplitude at one loop, the answer will give you 0 after integration, but not before integration. It will be the difference of two integrands with shifted momentum. So we will have what we call shift mismatches. And one of the things that we'll have to do is to cure this type of shift mismatches, to rework the word identities in such a way so that they don't appear. The other thing, which is even more bothersome, and it doesn't appear in soft collinear effective field theory, is that before you integrate out hard subgraphs, collinear gluons are not always longitudinal. In soft collinear effective field theory, if you represent hard functions with integrated Wilson coefficients, you never see this problem. But locally, it does appear. And finally, when we do if we solve all other problems, when we do ultraviolet renormalization with subtractions again, what we do should not spoil the work we have done before. Now, I don't want to bother you very much with all the details. I will spend 5 minutes talking a bit about the details, and then I should stop. I just want to give you a flavor of what is going on. So let's talk about the momentum flows. Why is it difficult? Okay. So suppose now I have a sum of Feynman diagrams in my two loop where they all contribute to the limit where this gluon labeled with K is parallel to the top external leg to the left, to the incoming quark. Okay? Now there will be this Feynman diagram, plus the cross Feynman diagram, plus the other, and you see them all when they come in. Now, what I want is that this gluon is named K. It has the same momentum flow assignment in all Feynman diagrams because all of them, they are going to be needed in the same word identity for the cancellations. Now, let's look at another collinear limit. Let's now look at the limit where the same gluon here, which appears in this Feynman diagram, is collinear to the other external leg, the bottom one. Then you would like, again, for this other singularity, other collinear singularity, the momentum assigned to the gluon to be always the same in all Feynman diagrams. But then notice, this Feynman diagram is the same as this one. And one collinear limit wants me to assign it the momentum K to this one. And another collinear limit wants me to assign the momentum K to the other one. So the white becomes the orange, and the orange becomes the white in the two. So they are exchanged. So if I assign momentum flows which are good for one collinear limit, I spoil them for the other. And what we ended up doing is to put a rule and say that the amplitude should be a symmetrized version of the two possible momentum flows. So this is one of our rules for constructing such amplitudes.
This is the integrand, right? It is not the amplitude.
This is at the integrand. Sorry, the amplitude integrand. Thank you. Now let me talk about another problem, and this is the problem of the fact that one loop word identities lead to cancellations that they are not local. The notation is slightly different because I took it from the paper. What I represented with the orange gluon here. So I have a gluon with an arrow, and this means a longitudinal gluon, a collinear gluon. Here is a gluon which becomes an arrow. It is the same object, just I changed a little bit the notation because I took this from the paper. Now let's look at the simplest amplitude, quark anti-quark to something, which is with a dot, some virtual photon or something. If you now look at, in this momentum flow, if you look at all the diagrams that they contribute, you see that the gluon attaches in all positions, and in the sub-loop here, it attaches here, here, and there in the 4 Feynman diagrams. Now, if you do the cancellations of the word identity, you will get a factorized term plus a difference of two objects. The difference of these two objects is the same integral, the same integrand, but in one case, the inner gluon has momentum L, and in the other case, it has momentum L minus K. When we integrate, this is fine, but locally, this is a mismatch. Okay, so we have to eliminate the mismatch. So I can tell you what is our solution. Our solution is to add something that cancels this mismatch to the amplitude integrand as a new rule. So what do? We take every planar diagram and we create two copies with two different momenta flows, and we subtract them. Also, this problem appears, let me go once behind. This problem appears because the gluon can attach to another gluon. And if you look at the color factor of these guys is a non-abelian color factor, it's Ca. So, but planar diagrams are abelian, so our copies, we have to reweight them with the right color factor. And when we do that, when we add this stuff here for every planar diagram made non-abelian, to have a non-abelian color factor as a difference, then it cancels exactly this mismatch. So this integrates to 0, so we didn't change the value of the amplitude, but we created an integrand where the word identity leads to local cancellations exactly. There are a few more problems. Let me skip that one. Let me go to something else, which is actually the most important one. Okay. So what I described to you in the one loop example was that if you have the particles splitting into two massless particles collinearly, then this gives you a longitudinal polarization for the gluon. Okay? Now, if you do it at two loops, and you allow that you have a self-energy, sorry, you allow that you have a vertex correction from this. So if this is hard, L is hard momentum, okay? Then still, this propagator and this propagator can have momenta which are collinear to the external leg. So there is a collinear singularity, but in here you have exchanged something hard. But this still exists. In soft collinear effective field theory, this would have been represented with a shrunk vertex. But here is not. What does it mean? It means that if you write the integrand for that, then not only you get the longitudinal polarization, K mu is the momentum of the collinear gluon, but you are going to get another vector here, L mu, which knows about the hard momentum in the subgraph, in the triangle subgraph. So, in the traditional proofs of factorization, you would integrate over L mu, and the integration would project L mu into K mu or P mu, which are the two which are defined by the collinear direction. So it would not have been a problem to show that things factorize after integration, but locally, this destroys it. And we thought that this could be the end of our journey, but then we added another 0 to the integrand. So what we do is to say that the one loop graphs should be associated with one more Feynman rule that corrects exactly for these loop polarizations. So whenever we have a one loop correction next to an external leg, we add one more graph engineered to do exactly that. Okay? So when we do that, we add another 0 to the integrand, we can make sure that this, what we call loop polarizations, which are not longitudinal, they do cancel. And in fact, I don't have time to go in these details, but in fact, what I want to say is that this thing cures other problems that they have to do with power singularities and so on. So it seems to want to be there. It's not something that, you know, it seems to be kind of a unique solution. So this encourages us to believe that we can reformulate our Feynman rules so that already from the beginning to have locally finite integrands without loop polarizations. So let me summarize what we have done right now, right? So I have done a few interventions. First, to choose momentum flows in a symmetrized way, which fixes what we call amplitude integrand, and added zeros. One was copies of planar diagrams that already exist in amplitude as differences. And the second was modification of vertices, one loop vertices in external legs. Once we've done that, then we can prove that all singularities, all collinear singularities, factorize locally, as we would like them to be in the theory. And now we can go if we want to make two-loop amplitudes finite, we can go and look at the simplest amplitude, the 2-to-1 form factor amplitude, for this kind of processes. Take its simple integrand, which is, you see these Feynman diagrams, plus 2 more for the Schiff-Cantor terms, and plus 2 more for 4 more for correcting this, and the other external vertices, and use it to subtract on singularities. So the final result of this work at 2 loops is as simple as that. Do these modifications, or follow these rules to write down the amplitude, and then all the singularities at 1 loop are subtracted, as we said, and 2 loops are subtracted if we remove the 2-loop form factor with an effective vertex, which is the 3-level amplitude, minus the 1-loop form factor with an effective vertex, pardon, which is the finite remainder that I have in here.
So is there some intuition of how systematic this can be?
So we hope it can become very systematic.
Because you said it seems to be there.
So this is exactly the structure that we anticipate from the factorization theory, when you expand it in alpha strong. Okay. Now, there are crucial questions. Can we really do it at higher order simple perturbation theory? Or before that, can we really do it if we have more than 2 colored particles? Or before that, can we do it when we have gluons instead of quarks? And we have started looking at all of these questions one by one. Let me define what I call success, okay? I admit that it may be a decades-long project to prove it at all order simple perturbation theory. But still, it will be very successful even if we stop here. If we stop at 2 loops. And for example, if we manage to add to that initial state gluons, and we are about to publish gluon initiated processes, glue to many Higgses via top quark loop. 2 loops, right. Yeah. And if we solve the problem of loop polarizations, these unphysical non-longitudinal polarizations for gluons, I think this will open a huge amount of processes that we can do, I mean, which are very, very important already. I hope that at 2 loops, it will not be very far. Already we can do physics with that. Already we can do WWZ with that. And I hope we can do, by adding initial state gluons and a soft, a bit more complicated soft function for the exchange of soft gluons among top quarks, we can do TT bar Higgs. So this would be already a success if we manage to do it. Right? But let me get you a little bit why I'm enthusiastic about it. I didn't expect that this would come out locally. I thought that we have to go diagram by diagram, make a local subtraction, and compute separately all of these subtractive Feynman diagrams. Now, when we do it in this way, this is also better for numerics, because all of these unphysical cancellations in collinear limits happen locally, so the integration does not see it. You don't need to combine fluctuating integrals, one very big against one very small, one with the opposite sign, sorry. So I think that this picture came out, it's a very encouraging thing. I consider it the beginning from the theory development, but I consider it also a very good step from the phenomenology side. But yes, I hope we can go further. Okay, I will not tell you about how we put ultraviolet on top of that, but it can be done, and I can discuss afterwards. I want to tell you that we checked all of that stuff. Many things could go wrong in our mind when we design it. And in fact, we had missed a few things, but when we implement things in before publication, of course. But when you check all the limits of these amplitudes, you see that they are finite, and we have done all these checks. And I want to say that there have been parallel work by many people on trying to integrate finite integrands numerically. Their problem is to avoid the singularities that they are not pinched, they are not infrared. These cut singularities, these threshold singularities, and they require a contour deformation. So there is a lot going on in this direction, but I will not tell you about it. One thing I want to say is that it helps to trivially integrate out the energy of every loop integration variable and using Cauchy's theorem that one can easily do, and this has a name. It's called time order perturbation theory or loop triviality or variants of that. But with this as a starting point, people have designed very powerful contour deformations that I think are very promising. So just to conclude, what I want to say is that in QCD we should not be sitting enjoying our success of having computing very complicated things, because what is coming next is more complex analytically, much more complex analytically than what we have ever experienced. And I think this calls for a different approach, which I advocated to be numerical. And this does not mean less thinking, quite the opposite. It means that we have to dig deep into the theory and understand completely the singular structure of amplitudes. And this is an attempt in this direction. Once we do that, I hope that we can design, as we have done in this class of processes, methods to build finite integrands and to compute without thinking very hard arbitrary processes at two loops in QCD. So thank you very much for your attention, and I hope I didn't, put too many details.
I want to ask a very general question. But in the factorization theorem, linear mapping, etc., the amplitudes are not finite, right? And you have to square them, sum over final states, so
yeah,
on average initial states. So there, so I must have misunderstood you when you get a finite amplitude.
No, you are absolutely right. The problem is that there are more than one factorization theorems, and sorry, let me get to that. So, and in fact, this factorization theorem for QCD was proven truly in the last few years. So for QCD, we know already from the works of Collins, Terman, and Soper of the 80s that when you, in wide angle scattering, if you put real radiation together with visual radiation plus parton densities, things become finite. Okay, and this was one of the factorization theorems. Now, with similar reasoning, without considering cut diagrams, but looking, without considering, for example, the optical theorem or what happens if you do a cross-section as a cut diagram, but looking at one side of the cuts, looking at the visual corrections, you can see what happens if you apply the similar techniques to the amplitude level. And what happens to the amplitude level is that the amplitude has all of these singularities. These singularities, I am not saying, naturally I should have been a bit more precise, I'm not saying that they are not there. I'm saying exactly what you anticipate, that once you combine them in a cross-section calculation, they will cancel in some way. Okay? And what it will be left over from the amplitude, it will be a remainder like this. And my goal has been to extract this remainder without going through them every time, again and again. So my goal was to use the simplest process, which is the 2-to-1 process, to account for all of these external factors, the infrared factors, locally, and to be left with only the hard.
Well, this hard could be written as a momentum integral of an integrand that's finite.
Absolutely.
I mean, free of integrals.
Yes, exactly. Thank you very much.